So welcome to my class, everybody. Today we will be discussing physics CIES. I made a previous video basically summarizing Newtonian mechanics, Newtonian physics. So now we will talk about some of the more discrete and abstract physics, known as waves and all that jazz, man. So first we will talk about electricity. CIES. Part 2 summary. Part 2 summary. Physics. So first we will talk about electricity. Electricity is basically the study of currents. First we had like stuff like a bit of electromagnetism, which may have studied in O level or IGCSE or GCSE, but now we will discuss about electricity mainly in AS physics. So we have electricity, which is electric current, which is rate of flow of charge, which is basically the flow of charges from one flow of charges in a circuit from one place to another, like a flow of charges, that is the definition, flow of charges per unit time. Something like this, that's represented with, let me just, so let me choose the other pencil, soft pencil, yeah, and change the color. So these are going through a wire. So current is basically I over QT or AS, which is the SI base unit. There could be other base unit depending on how it is used. Flow of charge per unit time. Flow of charge per unit time, electric current. So but first we will now study so basically first we will talk about how charges basically work. So we have these charges flowing, okay, you get that. Now next let's talk about their quantity, like how much quantity of charge per unit volume, which is basically the density of the charges. Like we have already studied in Newtonian mechanics, that density is basically mass per unit area. This is quantity of charge per unit volume or per unit area, per unit volume, quantity of charge per unit volume, okay, which will be n, and it will be v q minus 1, which is the SI base unit, IQ n q v minus 1, which is basically same as mass over volume is equal to p. Similar but not same. Next we will talk about a bit of other stuff, like quantity of charge. We also have mean drift velocity, basically how fast these electrons are traveling through this wire, which is mean drift velocity. This depends on length plus area. I mean cross sectional area, basically this part, cross sectional. Sorry for making this a lot messy. Of course you have like, see how it is. Mean drift velocity, which is basically how fast these electrons are traveling through this wire. Mean drift velocity, this depends on, this is directly proportional to length, no, cross sectional area of the wire, and inversely proportional to length velocity. So basically if we have this wire here, This is a bit short and a very long wire, and it has let's make this shorter, and then we have this wire. Let's make it a bit shorter, and that one, this is 2 times area, cross sectional area. This is 3 times length, 1 time cross sectional area. So we might have a ratio question like this. So basically this will have more mean drift velocity, 1.5 L. This will have more mean drift velocity, about 2 times more, 2 times more than here. Okay, so we have discussed this. Now let's move on to a formula. Basically quantized charge is basically charge of a single charge of a single carrier of charge, quantized charge 1.19. This is basically the charge for electron. 1.9 10 minus 16 quantized charge. So we have discussed till now. So we will have a formula like this: Na, which is number density, A cross sectional area, Q and V, cross sectional area, charge, velocity. So basically volume is basically covered by this, the number. If you multiply these, you will get volume. So it basically is like that. So we are covered till now. Let's talk more about let's see what else we can talk about. Let me just think about it. I'm finding it difficult to recall it, but we will now see. So there's also like uh, so we are discussed till now. Let's talk about resistance and potential difference. Potential difference, or which potential difference basically is related to EMF. EMF is the chemical energy, for example, stored in a battery wire, and which converts to electrical. So this PD is basically a phenomenon where basically due to conservation of energy, the energy is transferred into other forms, such as heat energy and light energy, or other energy from electrical to other form. Basically electrical and chemical energy to electrical, EMF, PD, electrical to other form, and these are equal because conservation of energy equal because conservation of energy, electrical to other form, equal because of conservation of energy. This is of course related to DC circuits as well, due to Kirchhoff laws, which will be discussed later. But now let's just discuss this. Chemical energy to electrical, PD, its unit is volt, and it is equal to IR, resistance multiply current multiply resistance. So we have this all mind mapped out like a brain dump. Current multiply resistance is equal to IR. Current multiply resistance so let's current is basically potential difference is basically the loss of energy basically dissipated into other forms while it is. Resistance is basically the ratio of V over I. V over I is equal to R. So basically we have discussed till now. let's discuss a bit about Ohm's law. It is basically like if we have resistance constant, then V and I will always be proportional. Always be proportional to each other. Proportional to each other, okay? So yeah, Ohm's law. Next, I'm kind of confused about what to teach you guys next, but let's see what I can recall from my mind and teach you guys. So Ohm's law. Next, we have some non-ohmic conductors. Non-ohmic conductors. Diode, thermistor, LDR, light dependent resistor, light dependent. Diode basically reverses the current. Basically, it is used in AC currents, which is discussed in DC circuits, and basically reverses the current. Reverses current, and can make it even. Make it even negative, due to infinite resistivity, because if there is infinite resistivity, no flow of charge, no nothing, and it will just stop. I think so. reverses and Reverses current and can make it even negative. So basically this is a diode. I don't know if it's like, I think it's like this. I'm kind of confusing this with CS logic gates, but yeah. Reverses current and makes it negative. Graphs are like this, like VI, so it will be like this and like this. This is positive, this is negative. I don't know about LDR thermistor. Basically, the higher the heat, more heat, higher the resistance. Resistance is basically a ratio of comparison of how much energy is lost while how much current is traveling through. So basically that's it. More heat, higher resistance. These all don't actually, I have to also get that these all don't follow laws of conductivity. More heat, higher resistance, LDR, light dependent resistance, also related to filament lamps due to similar properties. But I cannot recall how much these filament lamps are due to similar properties. Don't follow law of conductivity. If we actually discuss let's discuss a bigger summary, a more big picture of this chapter, electricity. Basically, charge at atomic level, current, properties of electricity. These two are both related together and cause uh, instruments, devices to manipulate electricity. Devices to manipulate electricity. Electricity. Don't follow laws of conductivity. Light dependent resistor, basically the darker the area is, darker the area around LDR, more resistivity or brightness. Basically, but there is no there is a unit for brightness, candelia, but we will not discuss that right now. So I have discussed all of this. Devices to manipulate electricity, don't follow laws of conductivity. Also we will I will also discuss about how these all ideas are basically related by all of this. This is basically let's talk a little bit more about potential difference, PD, or potential difference. PD or potential difference is basically the idea where we have something like basically we have already discussed this here, but we will now discuss it in more detail. Its unit is volt. V, it is measured with a voltmeter, and it PD or potential difference, voltmeter, and it measures basically it measures the amount of energy loss. It measures loss of electrical energy. Also, next we have DC circuits, which is of course related to all of this. We have electricity DC circuits, which is all related to the previous, because it's all about electricity. So of course there may be very nuanced relationship between them, not actually nuanced, but intuitive relationships which you can figure out. DC circuits basically means direct current circuits. Direct current. So when we talk about what actually happens, for example, if we have a circuit like this, this is negative, this is positive, and this is negative. Basically before I do not know the complete history, but scientists knew labeled something as now we label it as conventional current. Basically the idea that charges flow from positive to negative, but this is wrong, like not here, but we still use it in paper, in our own exams, and in daily life, in basically stuff like electrical engineering, because it's important to the idea that we have basically to not it's basically still there to remove to basically use for basically convenience. Okay, conventional current, this is wrong, and I actually flows like, okay, that's, let's say I, and charge basically we make E. DC circuits, direct current, conventional current. Sorry, I sneezed. Let me just take a tissue and finish this. Yeah. Conventional current. we drag current, commercial current, basically it flows like this. Next I will also discuss about how there are basically laws, Kirchhoff's law, which are basically laws, Kirchhoff's laws. So basically DC circuits is more about the nuanced electrical circuits, while the previous chapter was more about how electricity functions. Oh, okay, I missed a concept here. Let me just take it and revise it here. Power, electric power dissipation, which is basically how much electric current it's like ir square or v r square or like vr as equal power. Basically it's basically an idea how much power is dissipated due to how much resistance for the current. Okay, why is this important? Basically power and all these ideas are important because if we have too much resistance, the charge won't flow. Otherwise, if we have too less resistance, like zero resistance, the electric current like might blow up, and there might be hazards due to different ideas. So let's just move on. DC circuits, Kirchhoff's law. These laws are important because these laws discuss the idea of how basically they discuss how the circuits work. Kirchhoff's laws. How like current is basically first law. Let's actually draw it with an example here. So basically these are junctions. So if we have I1 here, then we have I2 here and I3 here. Basically it comes from I2 at a battery like this. We'll use even a battery for an example to make it more clear, and basically it will flow here, then it goes here and here. Basically the I1 is equal I2 2 plus I3, and we may have also other equations like V is equal total voltage, total potential difference voltage, IR I1 plus I R1 R2 plus I3 R3. So we can basically use this like if we reverse it, VR equal I VR1 VR2 VR2 VR3 R2. But if we do like this, we will basically get I R V3 R3. So basically if we cut this, we will get I over R. Basically this is for parallel circuits, which I will introduce now. Parallel resistors, parallel circuits is basically it's like they are parallel to each other. I will draw them in first. So if we have like this IR1 IR2 IR3. So basically if we take this inverse of all of this, we will get total resistance. It basically divided to each other if we take reciprocal of the resistance. Parallel circuits. Okay, we have discussed till now. So parallel circuits are kind of like this. Actually let's draw them even more parallel. Let's do a battery here. This is wrong, it's like this. So basically this is like are divided, but if we inverse them we will get a total resistance. So thing like that. Then we have series, which is basically non-parallel in one after another, like this this emf is basically the total voltage, like how much energy it has basically, and how much volt or ammeter is. So let's discuss about how IV characteristic, which is basically a graph which is related back to Ohm's law. IV characteristics basically for ohmic conductors, it will be a straight line. Let me draw a straight line using the smoothing tool. Okay, let's go like this. For ohmic conductors, let me now let me do this and take back to normal writing. So series basically it's like R1 total RT is equal to R1 plus R2 plus R3 plus R4. We also have something called terminal PD, which has a formula basically R1 R2 plus R1 over E. I don't know what is it. I will revise it and tell you guys later. But basically this gives terminal PD, which is basically the loss of energy at N1. Basically terminal PD is that at any point in a closed circuit, terminal PD equal to EMF. So basically if we don't have a closed circuit where electricity is just flowing everywhere, it will basically turn into a disaster, and it will be very bad, because someone can get shocked since the have no thing going on with them. I've discussed till now. Let's discuss a bit more. What else I can remember? There doesn't seem to be anything more, but resistivity of wires. I have missed this, but this is of course related to all of this. Resistivity. Basically this is resistance of a material of a wire. Like if we have copper wire, its resistance, for example, I don't know, because it's not necessary to memorize this as long as I know. But copper wire, let's say it has a resistivity of 10 minus 10 square meter 10 meter ohm minus 1 ohms. Resistance for SI unit is ohm. Basically V or I gives R. So copper wire, this is basically let's say this is resistivity, resistance R L over A. Resistance will increase. This is directly proportional. Length is inversely proportional, and this is also directly, actually no, this is inversely proportional. Actually this is directly proportional. And so we have done till now. So this part is done. I'm kind of overwhelmed at this point, so I might make these into separate videos, but I will try to do something about it. So let's go goodbye for now. I will talk to you guys later. Bye bye.